and welcome to the Spatial Structures Movers and Shakers interview series as we look ahead to the IASS Annual Symposium and Spatial Structures Conference taking place at the University of Surrey in August 2021. My name is Mark Richardson, and today I'm joined by Jan Knippers, who is a structural engineer and head of the Institute for Building Structures and Structural Design at the University of Stuttgart. Jan's research interests are innovative and resource-efficient structures at the intersection of research, development, and practice. Jan, thanks very much for joining us today.
Yeah, thank you, Mark, for inviting me and giving me the opportunity to share some ideas and thoughts.
No problem at all, Jan. It's a real pleasure to have you on the Movers and Shakers interview series. We start by asking our guests about lockdown. How has lockdown been for you in Germany?
So at the moment, everything is very, very quiet here, even more than it was last spring. So university is closed, offices are closed, everybody's at home. For myself, this is quite okay, I have to say. I can deal this pretty good, but I feel really sorry for all our students because they came here to study here. Many of them came from abroad, and they're now also sitting at home in front of their laptops. And all this kind of social interaction that is so important, in particular at the early stages of studies, is missing, and that is really, really bad, I think.
Yeah, thanks, Jan. A good summary of some of the challenges of the current period in higher education. We also explore our guests' career journeys and career paths. Perhaps you could provide us with an overview of your own career journey to date.
Yeah, I studied civil engineering. Or maybe I should start from school, because I had a strong interest in maths and also in arts. And I had also a strong tendency to study architecture, but there were no role models in my family. So I decided to go for this on the safe side and study civil engineering. And I studied civil engineering in Berlin. I did my diploma in '89, just a few weeks before the wall came down. And I also did my PhD in Berlin until '92. And at that point, I looked for a surrounding which was more creative and also more related to kind of cultural context, to kind of societal context. And at that time, it was in Stuttgart. So I went to Stuttgart because here are all of the great German engineers, like Frei Otto at that time and Jörg Schleich. And I was lucky that I was accepted at Jörg Schleich's office. I was one of the very first engineers there who did not study in Stuttgart, who came from another place. And this was really kind of very inspiring and motivating experience to work there for 7 or 8 years. But I always wanted to become professor, to be at university for research and for teaching as well. And it was kind of lucky coincidence that I was appointed here in Stuttgart in 2000. So I started in 2000 here at university already 20 years ago. And soon after that, I started my office, my first office, together with my partner, Thorsten Helbig, Knippers Helbig Advanced Engineering, that grew over the years and became pretty successful. But at a certain point, I felt that I have more to focus on the things that really matter for me, more on this kind of research-oriented projects. And I left this office, which is still pretty successful until today, and opened up the Jan Knippers Ingenieria.
Thanks very much, Jan. And you touched on there your latest venture. Perhaps you could provide us with a bit more background about how that's been going.
I think so. My career is a kind of I would say atypical career, because in Germany many professors have their offices, and when they get older, they spend more and more time in their offices and less time in their institutes at university. In my case, it was the other way around, actually, because I found research and also teaching as a very inspiring source of creating innovations. And I wanted to somehow link practice and research as close as possible. And that's why I focused on a kind of small research unit, small office unit that really brings research and practice together.
Brilliant, Jan. Sounds very exciting. Thanks for sharing the information about that with us. Well, we're now going to move on to the middle section of our interview, which is entitled Your Space, Your Structure. So at this point, I hand over the presentation rights to Jan, who will be taking us through a presentation relating to spatial structures on a topic of his choosing. So over to you, Jan.
Yeah, so thank you for allowing me to show some of our works, some of our projects. I first want to introduce the context of the projects I'm showing. I think that we in the building sector are facing these two challenges. On the left, you can see that the building sector is one of the main emittents of carbon dioxide, one of the main consumers of fossil resources. And we all know to fight climate change, we have to reduce this to a minimum. That's the one challenge. And the other challenge at the right shows that due to the growing world population, we have to drastically increase our activities, our building activities. So there are these kind of conflicting goals. On one hand, we have to use less resources, much less resources. On the other hand, we have to build much more buildings. So we have to drastically increase resource efficiency of our structures as well as the productivity of our building processes at the same time in a parallel process. But as you all know, there's another slide that many of you know, the productivity in the construction sector is stagnating or even decreasing. Yeah, in contrast to all other fields of technology where we have watched an increase in productivity during the last decades. And this low innovation, this low productivity growth is directly linked to the fact that the construction sector is the one that has the lowest digitization index. So we constantly talk about computational methods in design, but this is only about design, not about what's happening on site, on the construction site. These processes are still manual as they have been 10 years, 20 years, 30 years ago. So the discussion about digital methods in the building sector is currently very much shaped around the notion of building information modeling, but building information modeling does not question the process, the linear process as it is. It just tries to automate it and to make the design process still more efficient, more reliable, and more fast. And building information modeling also doesn't question the quality of the building itself that comes out of this process. And we think our key argument is that we have to break up this notion of a linear and hierarchical organized building process that begins with the design, then comes the engineering, and finally construction on site. And our key graph is what you can see here. We think that we have to, in a parallel and feedback-oriented and also open-ended process, have to work in a parallel process on design methods as well as on building processes. And only in this way we can create really new building systems that meet these global challenges that I was mentioning at the beginning. So we did it here in Stuttgart together with the group of Achim Menges and my group as a kind of collaborative endeavor. We did this kind of experimental buildings over the last decades. And the goal of these buildings is to show how this mutual development of computational design processes as well as robotical fabrication processes can lead to really new structural systems beyond the existing typologies that we have. And I want to go into this a bit deeper by presenting these two pavilions that we did for the Federal Gardening Show in 2019 in Heilbronn. You can see here at the back a fiber composite dome and here in front a timber shell. So two projects that we did together in our two teams in collaboration with an industry partner. And the aim of this first project, the carbon fiber dome, was to show how these investigation of robotic fabrication processes can lead to truly new innovative building systems. We know that fiber composites are used in many fields of technology where either weight or form matters, geometry matters. But usually they're fabricated in a way that we first build a mold, as you can see here, a mold often consisting of polyurethane foams, for example, resource-consuming fossil-based materials, and then we place a mat on it, and the fiber mat has a limited limited potential for adaptation to stress lines, and also leads to a lot of cutoff. And these kind of processes, fabrication processes, as you can see here, are only suitable for larger series. And I think that's the reason why fiber composites play a niche role only in the building sector. So we thought that we as architects and engineers have to develop our own fabrication processes adapted to the specific needs, to the specific requirements of the building sector. We don't have this maximum performance criteria as in the aerospace industry. We need simple, robust, reliable processes that allow for large-scale components that can be easily adapted to different geometries. Yeah. And what we did here is we developed this process with a rotating axis and a frame, and the robot places the fibers on this rotating frame without any molds and also without any cutoffs. So only as many fibers are placed, ideally, as you need to carry the loads. Here you can see it. We have here on top these two frames that can easily be adapted to different geometric configurations. Then we place here the glass fiber body, the hyperbolic glass fiber body. Glass fibers are cheap but weak. And then in the next subsequent step, we place black carbon fibers adapted to the loading of the components. These fibers are resin soaked, and then we put the entire package in an oven, cure it for several hours. What you get here is a composite structure that is able to carry high forces without a mold, without cut-off of fiber mats, only as many fibers placed as you need to carry the loads. Here's a video of the process. You can see the rotating frame, the resin-soaked wet fibers are placed here. It's real time. Here you can see the fiber spools. You saw the fiber spools pulled through resin bars and the rotating axis of the robot. Here again, the dry carbon fiber spools pulled through a resin bath. Here, a device to control the tension, spring, and then the fibers are placed on this rotating scaffolding. So what I want to say is that we as architects and engineers have to develop our own fabrication processes adapted to the needs of architecture and building construction. The structural design process happened in several layers. First, we optimized the overall shape of the dome by a simple grid model. We presented this at IASS 2019 in Barcelona. So the initial geometry was this sphere shell here, and it was then slightly distorted to reduce the bending moments in the components. Then we have a shell model to guide the fiber syntax, to guide the placement of the fibers and also the density of the fibers according to the stress lines. We also have models to calculate, analyze the loading in the respective fiber bundles. But what we cannot do, we cannot reliably predict the failure load of the components. So we are still relying on a larger series of large-scale testing. I find this pretty interesting because this large-scale additive manufacturing processes allow for a very differentiated load-adapted fiber layout, but at the same time you are thrown back to kind of pre-industrial engineering by trial and error, because these components are defined, the performance of the components is defined by so many parameters that cannot be reliably simulated. And what we did here is this large-scale compression test, and it revealed that these components that show a weight of 70 to 80 kg can carry around about 250 kilonewton compression force. This low weight facilitates installation, of course, no heavy formwork, no heavy cranes. We covered the whole structure by this mechanically pre-stressed ETFE foil of 700 square meters, which was an endeavor by its own. You can see the pre-stressed membrane, pre-stressed foil. And here you can see that these kind of fiber composite elements also provide a very different aesthetic, visual, haptic experience. The translucent glass fibers allow to guide light, to transmit light, to reflect light, also different, very different architectural opportunities. Final structure here and here from above as a role model for how the investigation of robotic fabrication processes can lead to completely new structural systems. And we are now at the threshold of transferring these technologies, these developments to practice. We're working on several projects that display the potential of these materials. Here you can see a facade where the fiber density is adapted to the orientation towards the sun and controls the solar gain. Here you can see a cantilever, 12 meters high, wind protection for a presentation area for Daimler-Benz. And you can see also here for temporary elements that are installed every year where the weight really matters. But the real potential I see is for on-site fabrication. We had this installation at the Victoria and Albert Museum in 2016 it was, where we displayed this idea of having a robot on-site coming only with a fiber can, with a resin can and a fiber spool, and the robot without noise, without dust, without dirt, produces from this very light and compact materials large and very strong load-bearing elements. So here we try to reduce the weight and the consumption of materials to a minimum, but we have to be aware that even then, even if we talk about light structures, very efficient structures, each building is related to an emission of carbon dioxide. You know that cement and steel, it's known to everybody that these are one of the main emittents of carbon dioxide. And even if we reduce the weight, if you design a very smart steel dome or concrete structure, we still produce a lot of CO2 emissions. And we only can turn this around by using this dark blue here, which is the carbon dioxide storage potential of timber structures. Here's this very nice graph from a scientific publication that was published last year that shows nicely that over millions of years, the carbon dioxide concentration in the atmosphere was reduced by storing carbon dioxide in the form of oil, gas, and coal in the ground. These resources were exploited since the beginning of the Industrial Revolution and transformed to concrete and steel structures. And this is linked to carbon dioxide emissions. So the concentration of carbon dioxide in the atmosphere increased. And if we want to reduce it, one of the few means that we have right now at this moment in 2021 is to see our buildings as storage of carbon dioxide by using as much timber as possible. So replacing carbon and steel structures by timber structures is a very important means to fight climate change. But if you look at current timber structures, you can see here, this is one out of many examples. You can see that it's possible today to build very high and performative structures, but the architectural range is still very limited. You can see here small and regular spans. You can see a lot of steel insert for the joints, and you can see that we still need concrete cores and concrete slabs for fire prevention. And the aim of the other pavilion, the second pavilion, the timber pavilion that we did in Heilbronn, was to explore how we can widen the range of potential application potentials for timber structures. We know that in particular here in this IASS community, that these concrete shells that were built in the mid of the 20th century are one of the highlights of spatial engineering, of lightweight engineering, but you don't find them today because the effort, the costs for their erection, for the scaffolding is so high that no one is willing to pay for it. And what we developed here is an alternative method by replacing the continuous surface of the shell by prefabricated planar segments, planar hexagonal segments, you can see here. We did also differ from this 19th century shells in a way that we did not look for the perfect shape. We more investigated which deviations from the perfect shape are possible, are allowable, to allow for more architectural design freedom. You can imagine that this kind of S-formed edges here are, from a structural point, not perfect, but they add a lot of kind of architectural quality, of expression, artistic expression to the shell. And we investigated here which deviations from the perfect form are possible. Here the shell has a span of 30 meters with this freeform shaped, and this was mapped by this planar hexagonal components that you can see here. And they all differ in shape and size, and this is only possible with a robotic fabrication, computational fabrication process. Here you can see the structural setup of the structure. These three layers are the load-bearing structure. So a top plate that carries all the membrane forces, this edge beams to transfer the forces from one segment to the next one, and the lower plate to stiffen and strengthen this cassette. And on top we had this drainage and the outer cladding. Of course, there was a kind of digital model that contained all information needed for fabrication. And what we did here is we had this mobile robotic fabrication platform installed in the shop of a small-scale timber manufacturer close to Stuttgart. And you can see here these two corresponding robots. On the left side, the one is picking and placing the parts, and the right one is processing them by drilling the holes, applying the glue, what you can see here now, and placing this temporary hardwood nails to fix the components. And then in the final stage, after curing of the resin, here you can see again the placement of the glue, the positioning of these edge beams, and here these temporary nails for the fixing, placement of glues, and What was very important here, also kind of surprising, is that we know from these concrete shells that the scaffolding is one of the main issues that is related with a lot of costs. And what we did here is we installed this shell structure without any scaffolding except of these three that we had here to support the edge beams. This is only possible because these components are very light but stiff, and this allows for installation without scaffolding, which makes this whole building system, very competitive in terms of costs as well. You can see again for all the forces are transferred by contact through this through this zigzag surfaces here. Only to carry the out-of-plane shear, we had to place some bolts. Here you can see that this was the last component after installing 30 meters of span, and it fit here without any problems. So this was only possible because of the high accuracy of the fabrication process. Yeah, only, as I said earlier, the placement of the bolts, this was necessary to carry the out-of-plane shear forces. And you can see here that this was a pretty painful work. And the next step is then to bring this augmented fabrication processes, these computational assembly processes on site, not only in the shop, but also on site. And this was the final structure as it was installed in Heilbronn and will be re-erected for the next gardening show in 2023 in Mannheim as a permanent building. Yeah, you can see from the inside, again, nice new architectural possibilities, pretty successful also because of its good acoustic performance related to this hollow segments that you can see here. Yep, I think this was already the last slide. Again, here we have to think of, as engineers and architects, not only of the design of the final structure, but also of the entire process, how to fabricate it and how to install it. I think this is the main message, and that computational methods offer a lot of opportunities here to create really new structures. That is what we are looking for here in Stuttgart. Also here we try to transfer this to practice, and we see the potential, for example, in extension of the existing building stock, because the structures are light and the geometry can be adapted to the existing structure. We see the potential in wide spanning structures made out of timber, and we see the potential also in temporary buildings, because these structure can be installed and deinstalled without affecting the performance of the system, of the components. Many people ask us, these are interesting shell structures, but what we have to have are new systems for multi-story buildings. And what our answer to this question is always that we see this pavilions as a kind of demonstrator to fully explore the geometric and the architectural and the structural potential of the systems, but that in a subsequent step we transfer these ideas to more regular building systems. So you can see here what we are working on now is on multi-story timber buildings using the same fabrication unit. You can see here the same idea of this hollow boxes with load-adapted webs, and we're trying to transfer these concepts that we explore for the shell structure to more regular multi-story building systems. And the same happens also for the fiber composite systems that I showed earlier. Okay, I think this was my last slide. Mark.
Jan, thanks very much for taking us through your presentation there. A fascinating number of topics covered. Particularly interesting seeing some very innovative applications of robotic fabrication. Thank you very much for taking us through that. We're now moving to the final section of the interview, which looks at the future of spatial structures. Now, a key theme of the 2021 conference is inspiring the next generation. What advice would you offer to aspiring engineers and architects looking to enter the field of spatial structures?
Yeah. I have to say from my personal experience is that I was not always a very happy student, to be honest, of structural engineering, because I was missing, as I said in my intro already, I was missing this link to architecture, to culture, to society. And for me, it was very important that I started my career in an environment that offered these things that I was missing. And I think the most important thing is, if you start your career, that you look for people, for offices, for an environment that inspires you, that motivates you. And I think that is in particular important in the very early phase of your career, because that's where you define the trajectories of your career. And I want to say that I think that these IASS conferences are particularly good opportunities, perfect opportunities, in particular for young engineers to meet the whole field of old professors, young PhD students, from theory, academics, as well as from practice. So I think the IASS conferences I always found very inspiring, because you had this whole range of people working on creative new structures.
Brilliant advice, Jan. Thank you for that. And I couldn't agree more with you. It's an excellent outlook on approaching spatial structures, particularly for young aspiring individuals. We've slightly touched on my next question in your presentation, but what do you think are the most pressing challenges in the field of spatial structures with respect to current global challenges?
No, I think that the generation of engineers before me, like Frei Otto and Jörg Schleich, for them always lightweight design was the guiding principles. They said a light structure is a good structure because it's using less resources and it's following timeless design principles. And today we know that the situation is more complex. If you build a light structure in Brazil for a stadium roof, for example, it's not necessarily a good structure. If it's not used later, if it was designed by European engineers, constructed by American companies. So we have to integrate in our design thinking the entire process. By whom is it fabricated? Which materials are we using? Which fabrication processes are we using? We have to consider, as designers, the whole chain and look for sustainable fabrication processes, for sustainable building materials. In particular, timber has to be promoted to make this step to more sustainable structures.
Superb. Well, Jan, thank you very much for taking the time to join us today on the Movers and Shakers interview series. It was a pleasure to speak to you. And thank you again for your presentation. Much appreciated and enjoyed. For those who are watching our conference video series, do be advised that registration for the conference is now open. Please head over to the conference website for more information. And if you have enjoyed our Movers and Shakers interview series, please remember to like, share, and comment. We welcome all your views. But for now, Jan, thank you for joining us today, and hopefully we can catch up with you again on the Movers and Shakers interview series as we move closer to the 2021 conference.
Yeah, thank you very much for having me.
No problem, Jan. See you soon.
Yeah, bye.